So, hi everyone, I'm Gabriella Edghill. I'm a master's student at Solent University, and today I'll be talking to you a little bit about my thesis on business interruption from flooding, which I did in collaboration with a company called Rebalance Earth, who I'm also now doing my work placement with. So, if you don't know about them, Rebalance Earth is a boutique fund manager here in the UK that treats nature as an investable asset class, and they focus on investing in nature reconstruction projects that tackle water related issues like flooding, drought, and water quality problems here in the UK. Their model is pretty straightforward. They get investment from major investors like the West Yorkshire Pension Fund to restore ecosystems. And their goal is to get local businesses to pay an annual subscription fee, like a subscription fee, to for the protection that these ecosystems provide. And the goal is also for the businesses, for that the revenue from that to go towards paying the investors back and giving them a return on their investment. Um, so for a business that is at risk of flooding, they might do something like, instead of paying for expensive flood defenses like a concrete wall, they would pay this subscription fee, and Rebalance Earth, knowing that Rebalance Earth will invest in a nature or river reconstruction project upstream from them, and that would protect their business from flooding. So to find businesses and also find investment opportunities, they built the Geospatial Predictive Analytics platform, which was entirely built on open source tools. It's an interactive web map that does a lot of things, but the main thing is that when you choose a flood scenario up on top here, and you draw a bounding box on the map, it shows you the flood zone in purple, and then all of the assets that are at risk of flooding. So businesses, buildings, substations, etc. Just for your information, this is Leeds, and you are sitting right here in the middle of this low probability flood zone. So the main point I want to make here is that what GPAP does, if you're talking in geospatial terms, it intersects the flood zone with the businesses and assets, and it only tells you what businesses are at risk of direct damage from flooding. But the innovative minds at Rebalance Earth wanted a little bit more from GPAP, and that's where I came in. So my task was to look at the secondary impacts of flooding and see whether we could use open source tools to assess business interruption from things like power failure from substation flooding and business interruption from road flooding, because businesses rely on power and roads for their daily operations. So I had three main objectives. The first one was to identify businesses at risk of losing power. And to do that, I performed spatial intersections with SQL. The second was to quantify the time cost of road flooding, and I used least cost path analysis with pgRouting to create a query that could calculate a route from a given business to a major motorway junction. And the reason for that is because if you can get onto a major motorway in England, you can get to anywhere in England. The third was to identify businesses cut off by flooded roads. And to do that, I used graph analysis with pgRouting to identify connected components in the road network. So just jumping right in, these are all of the data sets that I used for this analysis. You can see that most of them are from publicly available resources, all of it except for the businesses, which were purchased by Rebalance Earth. And then another thing to note here is that the power substations were compiled by Rebalance Earth from several different power companies. So that's going to come in a little bit later. These are all the tools that I use, and I'm sure all of you are going to be familiar with all of these tools. If you're not familiar with pgRouting, it's an extension that can be added onto PostGIS that has network routing and graph analysis capabilities. So jumping back to my first objective was identifying businesses at risk of losing power. But how do we know what areas are going to lose power? Well, we don't have data on the service areas for power substations in England. That's just not publicly available. So what we can do is you can use Voronoi polygons to estimate these service areas. And if you don't know, Voronoi polygons partition space based on a given set of points. So also a little bit of background on how power substations work in England. They operate on a hierarchical basis. So power generation stations provide power to grid substations, which send power to lower voltage primary substations, which send power to even lower voltage distribution substations, which then send power to our homes and businesses. And like I said before, because we compiled the data from a bunch of different power companies, we got things like mismatched formatting of the voltage levels and all of that. And all we had was information on their voltages. So we kind of had to do something with that. And what we ended up doing was we reclassified the data based on the voltage into categories: distribution, grid, and primary. And we created our Voronoi polygons based on that. So I used ST Voronoi polygons in PostGIS to do that, and these are the ones that I got for grid, primary, and distribution. And there's one substation for each of these areas. So these are the areas that we're going to see that are going to be, when we intersect them with the flood zone, we'll see what areas are at risk of losing power. So I had a pretty big query to identify the businesses at risk of losing power, but I will break it down for you. The first part of the query, the first step, was to create a bounding box that represents the area of interest. So I wanted it to act like GPAP, where I can draw a bounding box and put any coordinates in here. So I used SD make envelope to do that. And then in the second step, I intersected the flood zone with the substations, Voronoi polygons, and area of interest. So what I did here was I intersected the substations with the flood zone to get which substations are going to be flooded, and then intersected that with the Voronoi polygons to find out which areas are going to be flooded, which areas are going to lose power based on flooded substations. And then I intersected all of that with the area of interest so that I'm only doing all of this processing within my bounding box. The third step was to intersect the businesses data set with the affected Voronoi polygons to determine which businesses are going to be affected by power loss. So what I did was just intersect them and then intersect all of that with the area of interest. And then I didn't include businesses that intersect with the flood zone directly because I only want to look at businesses that are affected by power loss. So just a little side note, if you don't know what CTEs are, common table expressions are temporary stored results that you can use in SQL queries to build up a query and make it more complex. So you use a with statement here, and with my query, I used a with statement to create my AOI square. You can use a comma in between your CTE statements. And in the second CTE, you can also like reference your first one while you're creating your next one. And then in your final select statement, you can reference both of your CTEs that you want to use. So that's really a helpful tool that I learned how to use in the process of this project. So here are the results. If you can see here, this is the purple here, this is the flood zone. These diamonds are the power substations, and these areas here in yellow are the areas that are at risk of losing power because the substations are flooded. The red dots are businesses at risk of losing power, and you can see that even up to 75 meters outside of the flood zone, you have a business that is going to be affected by the secondary impacts of flooding. So that's really significant to Rebalance Earth. Here's another example. In black here, you have these businesses that intersect directly with the flood zone, so they're at risk of direct damages from flooding. But then these businesses in red are at risk of, again, losing power. So it significantly amplifies the number of businesses that are at risk. So jumping to my second and third objectives, how do we assess business disruption from road flooding? So we can use something called graphs. If you don't know about this, Graphs are an abstract representation of complex relationships and real-world phenomena, and they consist of vertices, which are these letters here, and edges, which are the lines. And if you use a graph to represent a road network, a vertex can be a road junction, a vertex or a node. I kind of use them interchangeably. A node can be a road junction and an edge can be a roadway. And we can have weights assigned to them to represent things like travel distance or travel time. And when we want to use least cost path analysis, we can try to find, if we want to find a path from A to G, we can use these weights to try to find the least cost path. And if we want to look at how it's impacted by flooding, like imagine there's a flood zone here around F, and we have to remove F and all of its surrounding edges. Now what's the least cost path between A and G? We have to go all the way around here to avoid that flood zone. So that's like a pivotal aspect of this study. And on top of that, when we want to assess disruption from road flooding, we want to figure out what businesses are cut off from the main road network. We can also use graph analysis. So if this is used to be a one single graph, and G and L used to be linked by one edge, imagine there was a flood zone here, but we removed that. Now we have two separate components. These are called connected components because all of the nodes within them are connected to each other. So that's another pivotal thing to my study. So how do we do this? How do we quantify the time cost of flooding? We can use something called Dijkstra's algorithm, which is a least cost path algorithm. And in pgRouting, it has something called pgRDijkstra. That's a function that we can use to calculate the least cost path. The function takes four things. It takes a query, which is used to select the network that we're going to use. It takes the closest road segment to your starting point, the closest road segment to your ending point, and a Boolean value to define whether the graph is directed or undirected. And a directed graph is a graph with edges that can only be traversed in one direction. And with roads, you have one or roads, and so it is directed. So this is the query that I use, or part of it, and it is kind of daunting, but I'm going to break it down again. You have the start roadway, which is the closest roadway to my starting point, which I identified as one of the businesses. You have the junction point, which is the closest motorway junction to the starting point. And then you have the end point, which is the closest roadway to the junction point that we identified in the step above. And then you have the main chunk of the query, which takes a subquery in here in quotes, and that selects your entire network. And what I did was I customized the query to not include flooded roads. So I say where not exists, and then I intersect the flood zone with the roads to remove those. And then I input the start and end like roadways that I identified in the first part. So this is the results that I get. This is in green here, we have a route between a starting point and a major motorway junction, and that's without flooding. And then in red here, we have a route with flooding. And you can see that it does a lot of windy roundabout things to avoid the flood zone. And down here, you think it might be crossing the flood zone, but this is a protected road here. So it can traverse that road. So like I said before, what I want to do is calculate the time cost difference between flooded and non-flooded routes. So that was just calculating the routes. But now I want to sum up the time cost in seconds for a flooded route. And I do that here. I just select the sum. And then I do the same thing for, I did that. That was a non-flooded route. Now this is a flooded route. And like I said before, I intersect the roadway with the flood zone. And then I subtract that to get the total time, the time difference between flooded and non-flooded routes. And what I get is a table that gives you in seconds the time with and without flooding and the time difference. So you can see that there's a 276 second time difference between these routes. But you might notice that there's something wrong with these routes, right? You might think, okay, if I want to get from here to here, surely I should just take this road right here. But my route does like a little roundabout way of doing it, and it just looks a little bit funny. And Google Maps confirms that. But the problem with my query is that I chose the closest node, that's at the endpoint of this roadway here, to the motorway junction in my query, instead of choosing the ideal node, which would have been the closest road to both the start point and the motorway junction. And that's something that's just a little bit, yeah, just an adjustment I have to make. So, side note, if you want to use routing, if you want to use a data set for routing, OS Open Roads doesn't come with a one-way or two-way routing or feature, so you end up with routes that look like this, where you go the wrong way around roundabout. So you want to use OSM Open Roads, which is what I did. The third and final objective was to identify businesses at risk of being cut off. And what I did was I used pgR connected components. And pgR connected components is another function that it basically also takes the entire roadway. And I did the same thing. I didn't include roads that intersected the flood zone. And this is the result that you get when you do that. And it looks a little bit like, what am I supposed to do with this? It's intimidating. Essentially, this table gives you the node IDs and the components that each of these nodes belongs to. And what I can do with that is count the number of nodes in each component and figure out which one is the largest one. And the largest component I considered to be the main road network. And then all of the smaller components I considered to be cut off portions of that road network. So what I did was I just kind of found businesses within 50 meters of all of the smallest components. And this was pretty successful. If you zoom in to areas where the flood zone completely surrounds a portion of the road network, the different colored roads are different components. So this is one component all on its own, and these businesses pop up as cut off from the rest of the road network. Some of the limitations here are the fact that I did this within an AOI boundary, and my AOI boundary ended up cutting off my road network, creating dangling edges, and also just kind of pizza slicing up my road network based on the AOI and also the flood zone. And this is something that also can be fixed by just kind of adjusting my query. So the implications of that are basically that Rebalance can now kind of target businesses that are impacted by the secondary impacts of flooding, including power loss and roads. And once we implement that into GPAP, then we'll be able to have better targeting methods. And yeah, that's it. If you have any questions, please let me know. So, any questions? Hi. Sorry. Right. Yeah.
Can I ask you to repeat the question?
Right. Repeat the question. Yes.
They've asked it.
Say it super loud.
Yeah, I'll just repeat it because I think I have to say it into here.
Yeah.
Thank you so much. It was super interesting. It feels like very impactful work as well.
Thank you.
I was wondering, after you conducted this
Mm-hmm.
why did you choose SQL? Would you use it again?
So the question was, why did I use SQL to do all of this? And the main reason was because, PostGIS with SQL, it comes with all of the functions. PostGIS comes with all of these functions. And then also with SQL, what I can do is customize those queries to not include areas where like roads are flooded or not include substations that are flooded. And so it just kind of gives me a little bit more of a customizable way of doing things. Yeah. Mm-hmm. Oh, yes. Hi.
How do you work with multiple orders? Because you mentioned substations at the start, that you've got the primary distribution, and your secondary substations. How do you deal with, obviously, on your model there, you seem to be working with primary substations, but do you deal with when a distribution substation is flooded, goes down, and knocks out the other substations?
So if a primary substation is flooded, then we assume that all of the distribution substations that it provides power, or well, we don't know which distribution substations it provides power to, right? But we just assume that all of the distribution substations, I guess, in the area that it, like its service area, are also going to be flooded, or sorry, are also going to lose power. We don't necessarily have like networking capabilities to model this, but we just kind of have to estimate it using the polygons. And that's something that this is kind of like a V1 that we're using. And this is the most simple thing that we could think of to do. And we will be, I guess, implementing more complex modeling later on. Yeah. Any other questions?
Yeah.
Oh.
With the PostGIS setup, like to create visualization, did you connect it to QGIS or directly inside any particular tool? The screenshots that are there.
Yeah, so this in the screenshots that I use, what you can do is, yeah, I connected Postgres into QGIS, and in the database management tab in QGIS, you can run SQL queries right in there, and then load the result onto a QGIS map. So it works really well for visualizing things.
Yeah, that's great.
Thank you.
This question about the voronoi.
Mhm.
What sense do you get that those voronoids are lost? Have you identified any potential data sources to sort of ground truth that? Get a sense of.
Yes. So sorry, I forgot to repeat the questions this
That's
whole
okay.
time, but right, the question was how do we validate the Voronoi polygons and if we're using any ground truth. We did find one data set that gave us service areas for some substations, or well, substations all around England, but we weren't sure what voltage level those substations were at. We weren't sure what kind of substations they were, so we weren't really sure if we could use that to validate the points. But in the image that I showed you guys of this, these Voronoi polygons, that these ones here, this was actually used by Western Power Distribution which was taken over by National Grid, and they actually use Voronoi polygons themselves to even estimate their areas. So I was like, well, might as well do it too.
They don't know where the power goes
So, yeah, so not really a best way to validate it, but yes. Okay.
One right at the back.
At the back. Oh yeah.
Thank you. I really enjoyed it.
Thank you.
Is available on a beautiful GitHub repository?
Not yes. Oh, the question was, is this available on a GitHub repository? It's not available yet. I actually just finished it, and I just started working for Rebalance. So we are going to be implementing it into our GPAP tool, which is also not quite available yet, but hopefully one day. I think the plan is to make it open source eventually. Yes.
I think that's probably all we've got time for in questions, but you're around for the rest of the...
Yeah, I'm around for the rest. So if you want to talk to me, definitely come and find me. Yeah.
Thank you.